That'll work. Okay. Thank you. And Luke's still gone, yeah. Notes are out. You guys are maybe going to struggle keeping up today. I don't think so. You should be good. You're going to be fine. It's going to be great. Yeah.
Anson, do you have a pencil?
I actually don't think so because I don't use pencils.
Yeah.
Well, sure. I don't know where it is. Oh, yeah, I got one right here. Good job not letting it stab you in the eye.
I've been stabbed by a cat's claw in the eye.
Oh, man.
That hole.
Like, wait, Flurvin from Marvel? Didn't they call the cat alien thing a Flurgan? Flurvin?
Yeah, I think it's.
Remember Agent Fury?
Yeah.
The eye thing?
Yeah.
He let it go and it got, like, terribly infected. Yeah, it doesn't have to be an alien cat. Like, I mean, the cats go in the doo-doo box and then cover their doo-doo with their paws. And you think they don't have things on their... Yeah. Okay. Attendance, wrong class. Yup. Nope. Nope. Bradbury's gone. But Riley's here, so it's all good.
Is it Wolf or Trey?
Sure. All right, cool. All right, so here you go. You guys know logarithms, right? You guys, your math skills are up to logarithm level? Don't know what a logarithm is? You do? No? All right. Show of hands. How many of y'all know how to use logarithms? Okay, don't even know what it is. So I am going to show you how to do like radiometric dating math without radiometric dating math. So if you look up at the screen here, they have it broken down using a logarithm. Okay, this is the formula, not terribly complicated, but you have to know how to use it. Okay, so because you're freshmen, you haven't gotten there yet, we're going to use elementary school math instead. Does that work? Okay. I am not qualified. I'm not a math teacher. I will not teach you how to do log of this and that and the other thing. Instead, we will use elementary math like addition. Can you guys do addition?
Yes.
Subtraction? Can we multiply?
Yes.
Can we divide? And finally, can we do fractions?
Yes.
Okay. All right. So here we go. First thing first. Right here, do we have that in our notes already? Yes. You already have the definition of a half-life in your notes. I know you do because I was here.
What?
I was like probably 3 weeks ago when we were doing the periodic table stuff. Okay. So as part of that, we were talking about how some elements have a radioactive isotope or version of that element. Okay. So radioactivity means instability. Yes. So an isotope is unstable. It will decay or break down over time. And on the board right here, I have a very short list. They've got a longer list on the page I pulled up from USGS. Very short list, just 3 decay series, just so you have a few examples in your notes. So put these in your notes. The decay series is a parent to daughter series, whereby we go from a less stable isotope, the parent, to a more stable isotope, the daughter. So the first example I have up here is the carbon-14 to nitrogen decay series, where we have beta decay going on. So we have a neutron breaking down to become a proton and an electron. Good. The electron gets kicked out. That's the beta particle. Cool. We talked about this yesterday. For half of the carbon-14 in whatever sample to break down into nitrogen, it takes 5,730 years. That's the half-life of carbon-14.
Dang,
Yeah, it's a long time. And there is only a relatively short list of decay series that are long enough to be very useful for aging things and stuff. So if an archaeologist found a bone tool out at a dig site, they'd probably want to use carbon-14 dating because that bone was once part of a living thing, yes? And life on Earth as we know it is what based? Carbon-based. Okay. So because we have the decay rate, because chemists way more intelligent than I have determined the decay rate, they've calculated that it takes that long for half of a sample to break down. Questions on that? Can't see because I'm in the way. That's why I try to move around so everybody gets a chance to see. Uranium-235 to lead-207 is a combination of alpha and beta decay. Yesterday I was like, yeah, it's alpha decay. Well, the first step from uranium to thorium is alpha decay. And then it does like this 2 steps forward, 1 step back type thing for a while until it gets all the way down to lead-207. I won't pretend to know how all that works because I don't. And that takes 704 million years with an M. 704 million years for uranium-235 to decay to lead-207 through a combination of alpha and beta decay. And finally, for our short list, potassium-40 to argon, also a combination of decay types. 1.25 billion with a B years for that decay for half of a sample of potassium-14 to decay into argon. Yes? Well, you weren't here yesterday. Could you copy notes from somebody?
not me.
Not you? Okay.
Also, his test ain't appealing.
Well, I haven't put it up yet. I forgot about you.
Yeah, that's what I was about to ask.
Oh, that's what you're asking me. Okay.
Yeah.
Well, I'm sorry. I was getting teaching the rest of the class. Yeah.
I'll say, like, am I supposed to be taking notes or?
Yeah, you're gonna have to take the test and do notes at the same time. So I'm making a video of this, so I would rather you focus on the test. So I'm sorry, I just didn't get you started. So let me pull that up. Everybody else just stand fast for a moment. I got to get the right one up. Oh.
Okay, question. I'll do notes, but I don't think you can read my hand.
Come on, pull up. Sorry, internet's being slow. Shh. What do you need? Yeah, like, wait. No notes. All right. 5th period, right? This is 5th period, right? Okay.
I think
Awesome.
maybe.
All right. Shh. Back at it. Do you have a question?
Yeah.
What's the question?
Why do we use half-life?
So half-life is a measurement, okay, that could, well, short answer is you're about to find out, or longer answer, because we're going to use it. We're going to put it to use, okay? So hopefully after we put it to use, you'll be like, oh, okay, that makes sense, all right? So everybody good on the decay series chart? I'll leave it there, but I don't want too many of you like still doing that while we're getting started on the next thing. Yes?
How come we don't like do the whole life instead?
Because you're going to find out. Ask me that question again in about 10 minutes.
What time is it right now?
It's because it's indeterminable. But you're going to see that here in a moment. Okay?
How would it be independent?
You're going to see that in a moment. No, it's not what you think. Just trust me. You'll see. All right, we good? All right. So what I'm going to do now is I'm going to take just carbon-14 to nitrogen, that decay series. We're going to work with that one today to get started, okay? So we're going to make a chart. Does that go all the way over here?
Yeah.
Awesome, thanks. We're going to make a chart of known things about carbon-14 nitrogen. So carbon to nitrogen chart of known things. And it has 3 columns. So it's going to look like that. A T chart, but with 2 vertical pieces. The first one is the number of half-lives gone by. Sounds like a bad soap opera. Half-lives gone by. No. And it'd be like 0, 1, 2, 3, 4, and 5. In the middle column, you'll have a fraction, and it is parent isotopes over parent plus daughter isotopes. And finally, the right column is going to be the age of the sample. Everybody good? Fantastic. After no half-lives have gone by, no half-lives have occurred, I guess is how you'd phrase that, question mark. What would the fraction be of parent over parent plus daughter isotopes? Let me ask you a different way. How much decay would have happened after 0 half-lives have gone by? None, right? So if none of the parent isotope has decayed, what would the fraction be? 1 over 1. The whole amount of the total parent and daughter isotopes, all of them would be the parent still. So it would be 1 over 1. The whole of the sample is still the parent isotope, 1 over 1. Does that make sense? Okay. If all of it is still the parent isotope, none of it has decayed to daughter isotope yet, what is the age of the sample? 0. No decay has happened because there hasn't been time for any decay to happen. Does that make sense? Awesome. After 1 half-life for carbon-14, what would the fraction be? 1 over 2. 1 half life. 1 half. That means half of the parent isotope is still there in the sample. The other half has decayed to become the daughter isotope, nitrogen. If that's the fraction, what is the age of the sample? 5,730 years. How do we know that? Because you're given that. We know the half-life. We are given the half-life of carbon-14. Okay. Another half-life goes by. How long is the half-life for carbon-14? 5,730 years. Okay. Another half-life goes by. What would the fraction of parent over total isotopes be now?
1, 2.
What is a half of a half? 1/4. I know. I was waiting for everybody else to get there. I do the whole questioning look thing to make you doubt yourself a little bit. So check it out. So to cut a fraction in half, the short way of doing it is just doubling the denominator and leaving the numerator the same. Okay? So what would the age of the sample be after 2 half-lives?
11,460.
Okay? And what would the fraction be after 3 half-lives?
1/8.
An eighth. And what's a half of an eighth? And what's a half of a 16th? 1/32. Okay. How old would the sample be after 3 half-lives?
17,000.
And after 4? And after 5? Somebody else?
28,000.
Somebody else. Riddle. Riddle me this. I'm sure you've never heard that before. Shush. Yeah, then I asked for a specific person. What was it? All right. Guys, this is our chart of known things about carbon-14 and nitrogen decay. We can refer to this whenever we need. It's a chart of known things. All right? It's like the periodic table. I personally don't need you to memorize the periodic table because it's there. It's a resource. Use it. This is a resource. Okay? So we're going to do a hypothetical now. Hypothetical, we have a sample of that bone we were talking about. Okay? So we went out on a dig and we ran across this bone. Looks like it had been shaped into a tool. All right, cool. How old is it? In other words, how old is or should say, how long ago did the animal die that bone belonged to? Does that make sense? So we send it to a lab. They have a mass spectrometer. They take a sample of it, throw it through the machine, and it spits out numbers. And we're gonna invent our own numbers. Okay, we're gonna invent the numbers and put it in the fraction. So somebody give me a number between 10 and 35. I heard 28 first. All right. Shh. Remember, it's going to be parent over parent plus daughter. That's the fraction we have, all right? So we made up the total number of isotopes in the decay series. It's been simplified. Okay, obviously the numbers would be bigger than this. So that's the total. Now, how many of them out of those are parent isotopes? Somebody give me a number between 2 and 14.
7.
I heard 2 first. Shh. So 2/28 is our fraction. Now, why didn't they simplify it all the way for us? 1/14. Okay. So the lab, for whatever reason, they simplified it to 2/28. I don't know why they didn't go the rest of the way. So we went the rest of the way. 1/14 is our sample's fraction of parent to total isotopes in the decay series. Does that make sense? Everybody follow? Okay. If at any point I lose you, you got to say, whoa, you lost me. How'd we get here? What we need to do to determine the age of our sample first, without using logarithms, is to compare. Where does 1/14 go in our chart of known things?
Between 3 and 4.
Between 3 and 4?
Half-lives.
Between 3 and 4 half-lives? So we're guessing, or maybe you did the math that fast. You're saying that 1/14 goes between 1/8 and 1/16. Okay? So let me ask you this. What is half of, I'm going to go through the whole process with you, okay? Just in case we weren't guessing correctly. What's half of 14?
7.
Is 1 greater than or less than 7?
Less.
Less than. So we know our sample is less than a half. Okay. Is it less than or more than a quarter? So what's half of 7?
3.5.
3.5. Is 1 greater than or less than 3.5? Less than. So it's less than a quarter. What is half of 3.5?
1.75.
1.75. Is 1 greater than or less than 1.75? Less than. So it's less than an eighth. What's half of 1.75?
0.
Less than 1, right? So we know you guys are right. It goes, we're just confirming some of them are not so simple. Okay, sometimes the fraction you're like looking at, like, you have to do something like that to figure out where it goes. How else can we figure out where it goes? Could you convert this to a decimal and those to decimals? You could do that too to figure out where it goes, okay? Just be aware you can do that if you need to. All right, so we know it goes in here. What does that mean practically? We're trying to find out the age of our sample. What have we just done?
We've
Yeah, we've got a range. We know it's somewhere check out what I'm doing here. Follow along. We know it's somewhere between 17,190 and 22,920 years old. What are we making? A visual representation. This is a timeline, right? And then we can attach our fractions. This is 1/8. This is 1/16. Yes? Okay. And we have 1/14. Would it be maybe easier to work with this visually if all three of these fractions were on the same denominator? Okay, let's find the least common denominator. 14, 8, and 16.
4.
Guys, 16 can't go into 2.
Oh.
Go the other way.
Oh, I'm not.
What is it?
48.
48? Does 16 go into 48?
Yeah.
How many times? Does 8 go into 48? How many times? And does 14 go into 48?
I don't know.
Does 14 go into 48?
No.
56? Does 16 go into 56?
Yeah.
Evenly. Yeah?
Okay.
Does 14 go into 56?
Yeah.
Yeah?
With 16 is evenly. It's like
Oh, it doesn't go in evenly. Okay. So, okay, let's keep trying.
16 goes into 4 or
Guys, couldn't we just multiply 14 and 16 and call it a day?
yeah, 224.
What is it?
224.
224. So we're going to say 224ths, 224ths is going to be our denominator. Might there be a smaller one? Huh?
Should be 1.
What?
Just times 14 times 8.
So 224.
Yeah, because
Yeah.
What?
You can do 14.
Is 14 times 16 224?
Yes.
Okay, we're just going to run with it. All right? What is 1/8 of 224? It's not complicated math, y'all. What's 224 divided by 8? 28. What is 1/16 of 224?
14.
What is 1/14 of 224?
16.
So you take that divided by that, right? We're reverse engineering what we already did. Okay, guys, what is the difference between 28 and 14?
2.
2?
4.
Difference.
14.
14. So there's 14 pieces we're going to divide this into. Watch this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pieces. Everybody following?
Yeah.
16, 14, 15, 16. Our sample goes right there on our number/timeline. If it were all the way at the end, it'd be 22,920 years old. We are 2 pieces from that. Pieces of what? How much time is actually on our timeline total? What is the half-life of carbon-14?
5,730.
We just divided that into how many pieces? 14 pieces. Do the math. 5730 divided by 14.
What do we round?
No, just give me the number.
409.
409?
409.
0.28.
Okay, that's fine. I don't mind rounding to the nearest hundredth there. All right. Shh. So what does this mean? It means each of these increments is 409 and a quarter-ish, okay, years. We are 2 of those away from 22,920. So what math would I do to find the age of our sample?
Subtract.
I could subtract 409.29 twice from this, or I could multiply that by 2 and then subtract it from that. Or if I wanted to be further distance, I could say, well, what's 16? What's the difference between 28 and 16?
60.
The difference between 28 and 16. Is it 12? So I could take 409.29 times 12 and add that to 17,190. See how you could attack it from either end? Okay. So whichever one you want to do. Let's just subtract from this side. So we have 22,920 minus what is 409.29 times 2? 800 and what?
818.
Okay. So what's 22,920 minus 818? 22,1.
0 is 1.
Okay. So our sample age, 22,101. What about the decimals? We're talking about months here. Okay. It's okay to round. All right. So 22,101-ish. Does that work? We're close. Yes.
So I understand how we got the 5,700 divided by 14. Why do we times by 2?
Because we are 2 of those, 1, 2, away from the end of the timeline. So we just subtract 2 of those off to get our age of sample. Who else has a question? Everybody's good? Let's do another one.
Yes.
No?
Yes. It's go back to
Make sure I understand.
Yeah, do you want to walk through it all together? Let's walk through it. What did we just do? All right, we finished up, we created a chart of known things about carbon-14 decay. Yes? Okay. Any questions on the chart? All right. Next, we just created at random a fraction of parent over total isotopes in the sample, in the decay series. Okay? Then we took that fraction and figured out where it goes in our chart of known things. And then we took the one above and the one below, tilted it on its side to open it up into a number line. A number line that is also a timeline. Yes? Next, we got our fractions on the same footing. We put them with a common denominator. Okay? And because we've got them on a common denominator, it gets really like clear real fast. So we've got from 14 to 28, 16 is just 2 up. Make sense? Yes. This is the same fraction as far as value as that. See the equal signs? 2 28ths is equal to 114 is equal to 16 2/24. They mean the same thing. Yes.
Actually, the 81.8 or whatever.
818 is 2 times the 409.
Oh, okay.
Each increment, right? Okay, so we skipped. So we got that. We figured out where our sample goes. I did skip another one. So we divided our number line / timeline by the difference in the numerators on each end. So we said that between 28 and 14, there's 14. So we made 14 increments. Ours went right here. We said, well, we did it physically. Now we have to do the math of dividing the 5730 by the 14. So each of the increments is 409.25-ish years times the 2 from the end. And we subtracted that from the 22,920 to get our sample age. Want to do another one?
No.
Yes, we're going to do another one. All right. Like it or not.
Why didn't we
I still don't understand why you can't do like 2 half-lives equal a whole.
But it doesn't work. Oh, thank you. Shh. Hey guys. So she says, well, don't 2 half-lives equal a whole? No, because you'll end up just getting a smaller and smaller and smaller fraction, right? Because it's a smaller, you'll never get to 0, right? In real life, will you ever get to the point where all of the parent isotopes have decayed? Yeah, theoretically, eventually you'll get there, but we can't put our finger on it. Does that make sense? Because you never get to an end. Does that make sense? The denominator just gets bigger and bigger and bigger. Yes?
You approach 0, but you never hit it.
Exactly. You approach 0, but you never quite hit it. It would look like this on a chart, right? And with this being the baseline, and you'd get ever closer, but you'd never quite get to 0. Yes?
So, just make sure I'm understanding this correctly. So for every half-life, it's a half of the previous. And it takes, at least for that one, it takes around 5,000 years for each half to go to another half.
Yep. For another half of what's left of the parent isotope to decay away, it takes another 5,730 years.
Why is that?
Makes sense because there's less.
There's a rate of decay that chemists a lot smarter than me have worked out, and that's what it equals to.
Even though there's just a smaller amount of the previous, it'll take that amount of time to still get half of it.
It doesn't matter the size of the sample.
Okay.
Just whatever that size is, half of it, it takes that long for it to decay away.
So I feel like wouldn't it take longer for a big
Nope.
amount?
Nope. All right, check it out. Shh. Let's read this real quick. Might be helpful. It says a chemical element consists of atoms with a specific number of protons in their nuclei, but different atomic weights because we have various isotopes of those, right? Different number of neutrons. It goes on. Atoms of the same element with differing atomic weights are called isotopes. We just said that. Radioactive decay is a spontaneous process in which an isotope, the parent, loses particles from its nucleus to form an isotope of a new element, more stable, known as the daughter. The rate of decay is conveniently expressed in the terms of an isotope's half-life, or the time it takes for half of a particular isotope in a sample to decay. Most radioactive isotopes have rapid rates of decay, really short half-lives, and lose their radioactivity within a few days or years. Some isotopes, however, like the ones we're dealing with, decay more slowly. Several of these are used as geologic clocks, or in the case with carbon-14, to determine how long ago something died. The parent isotopes and corresponding daughter products most commonly used are listed here. I don't know if that helps, but yeah. Chemists that have more knowledge than me. You, young lady, have a chemistry mind, I think. So you're really going to like 2 years from now when you take chemistry. I'd recommend if they offer a dual credit, take the dual credit. Yes. Yes. All right. Let's run another example. Somebody give me a number between 35 and 50.
41.
17's not between 35 and 50.
41.
You guys, gluttons for punishment. 41. Okay. Okay, you wanted 41. Somebody give me a number. So that's going to be our parent plus daughter. Somebody give me a number between 2 and 20. I heard 17. That's not between there. You're just looking for a reason to be silly and disrupt class. And if you want to continue doing that, I don't know. What do you want me to do to you? Right up? That's silly. Just get over it. All right, so 17 over 41. Can we simplify that? No, why not?
Because 17 and 41.
Aren't they both prime? You guys are horrible. All right, so here we go. We can't simplify it. But hey, that could happen, right? They send us results and it's simplified down to a couple of prime numbers. Okay. Where does that go in our chart?
Between 5 and 6.
Wait.
Between.
I don't change. It'll be between
No.
32 and 64.
What are you supposed to do with the 17?
Guys, guys, this is, don't overcomplicate it. What's half of 41? 20.5. Is 17 greater than or less than 20.5? So it's less than a half. What is half of 20.5?
10.25.
10 and a quarter. Good. So 10 and a quarter. Is 17 greater than or less than 10 and a quarter? Great. So it's less than a half, greater than a quarter. Was that hard? No. So we figured out where it goes. Okay? Now that we have done that, what's next? Turn it into a number line / timeline. So we're going to go ahead and throw that up there. And we're going to have a quarter on this end, a half on this end. Guys, if I had students that were like, well, why can't I do it the other way? Well, you can, but if we're all doing the same way, it would make more sense, okay? So anywho, also going that would be further back in time, and some people want back in time to go that way. It's whatever you do, okay? I've always done it this way. I'm just trying to be consistent so I don't get confused up here, okay? So over here, this would be 11,460 years old. This would be 5,730 years old. The total amount of time on our timeline is 5,730 total from end to end. We are going to be dividing that. To find out what to divide it by, we need to do what with these three? Find a common denominator. So 41, 2, and 4, what?
82.
82? You want to do 82?
Yes. That's easy.
All right. We want to do 82. What's a quarter of 82? What's a quarter of 82? What? 0.5? So can we use 82? What could we use?
164.
Just double it. Yeah, 164. You guys want to get all mean about it? It's not that we got closer, right? All right. Shh. All right. Shh. I like it. Guys, could we have used 82 and had a decimal? Sure.
What?
Okay.
Should I left the decimal?
Could we have made it work?
Yes.
All right. Sometimes math rules are there and can kind of be broken and still get the right answer. Okay. All right, here we go. But we're gonna follow the math rules. Okay. We don't have a decimal in our fraction. So what's half of 164? 82. Good. See, the math wasn't for naught. What's a quarter of 164? 41. And what is this?
4.
4?
4 over.
Huh? What did we have to do? What did we have to do to go from 41 to 164? Times 4?
68.
68? All right, so 17 times 4 is 68. Is that right?
Yes.
Okay. Now we can go ahead and put it on here. What is the difference between 82 and 41?
41.
Here we go. I need 41 increments, which means I need 40 tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Sue me, they're not even. If you back away enough, it's like, okay, that's all right. All right, shh. So, 41 to 82, ours is at 68. 41 Or I could go backwards. Should I go backwards?
Yes.
Or could I go 82 minus 68?
Yep.
What's 82 minus 68? 14. So now I can just count to 14, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Our sample goes right there. All right. We have divided it into 41 pieces. We need to divide it into 41 pieces. Go ahead. Shh, don't blurt it out. Let everybody get a chance. Sears is waiting with his arms crossed, waiting for anyone else but him to do the work. Nice smiling about it. That's good.
How much is between both of them again, the lines?
Say again?
How many lines are between both?
I had to make 40 ticks to make 41 increments. Does that make sense? Because I already had the ends.
Forgot what it was.
That's what I said.
All right. Shh. Ooh, we got a heated debate going on. You know you're in a group of nerds when you're arguing over numbers. All right, so what's the number?
139.
130.7?
9.7.
0.67?
0.8.
0.8?
7.6.
All right. Shh. Are we happy with that?
Yeah.
All right. So each of these increments is 139.8, almost 140 years each. Okay. So 139.8 times how many did we say? 14. Equals what? 139.8 times 14. 1,000. Is that our answer? This is not our answer. This is how many years are between here and here. Right? That is 1,957 years right there. Yes. So we want to add this to our start point. So what is 5730 plus 1957?
7,687.
So our sample is 7,687 years old. Want me to walk you through it? I got one person just came back. Let's walk through it for her. All right. Shh. And do we have time? Yeah, we got time. We got 2 minutes to walk through this. We started with our chart of known things. We were given a fraction by the lab, 1740 firsts. We figured it goes between a half and a quarter. We opened it into a number line. We got a least common denominator, 164ths. We divided our timeline by 41, which is the difference between the two numerators on either end. And then we said, well, we're 10 away from, or excuse me, 14 away from the end. So we divide the whole thing by 41 and multiply that answer by the 14 to get this chunk of time, 1957. And we added that chunk of time to the 5730 to get the age of our sample. Are there a lot of steps?
Yes.
Is it hard math?
No.
Okay, yes.
So, because I forgot the very beginning, we first get the fraction, then we're supposed to find each.
Yeah, let's see where it goes, where it fits.
Yeah, how do we do that again?
Mr. Young?
Well, in this case, we just said, hey, well, what's half of 41? And if this is less than half, then we're less than a half on the chart. Does that make sense?
Literally, Harrison.
Because 17 is less than half of 41, but it's more than a quarter of 41. So it goes in between a half and a quarter.
What's up?
I'll never get used to it.
I think you will. So we're going to do a bunch more.
These two get as soon as they kill.
Go to lunch!
And add